Okay, in this video lecture, I want to talk about vectors. So this will sort of be our application of trigonometry. So vectors. Actually, let me do this in black. So many quantities in math, physics, engineering, etc. are represented as vectors. So many quantities in math, physics, engineering, etc. are represented as vectors. So you can think of a vector as something that has both a magnitude and a direction. And usually you represent a vector, at least graphically, as an arrow, right? Or sometimes people say a directed line and segment, but you can think of it as an arrow. So like this vector f here, and usually you put a little arrow over the top to represent the fact that it's a vector. If you read a vector in a textbook, sometimes it's in boldface, so that also means a vector. So again, it has a magnitude, so let's say it has a magnitude, which is represented by the length of that arrow. And it has a direction. Right, which is given by the sense, right, of that arrow, the direction of that arrow. Now, usually, if you want to give a particular, like a numerical value for the direction, usually you'll plot your vector in a Cartesian coordinate system. So, for example, this is like our standard Cartesian coordinate system. Let's say I have a vector A. Okay, so this is my vector A. And the direction would be given by the angle, and usually by convention it's measured like we typically do, right, from the positive x-axis counterclockwise. So let's say this is the angle, let's say it's 65 degrees. So in this case it would have a magnitude, right? So the length of that vector would be some value. Let me just give it a value. By the way, to represent the magnitude of the vector, you can either use the name of the vector without the arrow on top, so like A, right, by itself, or you can either put one or two vertical lines. I think this, my Open Math uses two, so let me do it that way. So if I do like double vertical lines around the actual vector A, that also just means the magnitude of A. Okay, and this is equal to, I don't know, let's say it's 17.5. Let's say it's a force vector, so this is newtons. Okay, so this is magnitude. And then the direction is given by the angle. So in this case, let's say the angle is, what I have, 65 degrees, right? So it has a magnitude, the length of the vector, and it has a direction given by the angle. Typically, it's measured from the positive x-axis counterclockwise. Okay, another thing that's useful is vectors can be resolved into their x and y components. Okay, this will be really useful when we talk about adding vectors together. So vectors, let me go to a new page to do this. So vectors can be resolved into their x and y components. So let's say I'm given some vector, let's call it b. And I'm going to assume in this case it's a velocity vector, just as an example. So is a velocity vector. So a velocity, right, is a quantity in physics or engineering that has both a magnitude and a direction. And let's say that the magnitude of b is equal to 41.20 meters per second. And let's say the direction, the angle, so from the positive x counterclockwise, is 23 degrees. Right? So it has a magnitude and a direction. So what we want to do is we want to find the x and y components of vector b. So let me draw this out and show you what this means. So here's my Cartesian coordinate system. So this is x, this is y. B is going to look something like this. So there's my vector b. And I know that the length of that vector, right, is 41.20 meters per second. And I'm also told that this angle, right, measured from the positive x-axis counterclockwise, is 23 degrees. Now, when we talk about resolving the vector into components, x and y components, what I'm doing basically is I'm starting at the tip of b. Let me draw this a little bit better here. The arrow's off a little bit. So I start at the tip of b, the tip of the arrow, and I project a line down to the x-axis that's perpendicular to the x-axis. And then this distance now from the origin out to that line, that's going to be my x component of b. So I'll write it b sub x, so x component. And then if I project a line from the tip of the vector onto the y-axis, so perpendicular to the y-axis like this, then this value here that's vertical, that's going to be my y component of b. So I'll call it by. Okay, so the goal often is to figure out the x and y components of a particular vector. Typically, you have to do this first if you want to start a problem, if you want to ultimately add vectors together. You need to first find their x and y components. Okay, so how do we do this? Well, notice here that I have a right triangle, right? In fact, usually when you extract a right triangle, you want to extract the right triangle that includes the reference angle. Remember, that's the angle that the vector makes with respect to the x-axis. So in this first quadrant, it is just this angle, right? So this is the right triangle that I want to extract. Okay, so let's do that. So here's my right triangle. And I know the hypotenuse. The hypotenuse is the magnitude of that vector, right? So the hypotenuse is 41.2. And really it has units in this case, right? And since it's a velocity, so meters per second. I know this angle is 23 degrees, and this is b sub x, and this is b sub y, right? My two components I'm trying to find. Okay, let's try and find bx first. Well, how does that side bx relate to the angle 23 degrees? So how does this relate to the angle? Well, it's adjacent, right? It's adjacent to the angle. And in the 41.2, that's the hypotenuse. So what trig function relates adjacent and hypotenuse? That would be cosine, right? So katoa, so ka. So cosine of the angle is equal to adjacent over hypotenuse. So I know in this case that cosine of 23 degrees is going to be the length of the adjacent side bx over the hypotenuse, 41.2. Then if I multiply both sides by 41.2, on the right-hand side, the 41.2s will cancel. And I'm simply going to get bx is equal to 41.2 times cosine of 23 degrees. So that you would just plug into your calculator. Make sure that your calculator, that the angle is in degrees and not radians. Right now we're using degrees. So 41.2 times cosine of 23 is around 37.92. And then, again, it has units, right, of velocity, so it's meters per second. Then to get the y component, by, well, this side is opposite, right, of 23 degrees. So now I know opposite and hypotenuse. Or you could even use opposite and adjacent since we do know bx now, but it's easier just to use what you originally had. So opposite and hypotenuse. So what trig function relates opposite and hypotenuse? That's so, right, sine? So I know that sine of 23 has got to be by over 41.2. And now if I multiply both sides by 41.2, that'll cancel. And I'm going to get by is equal to 41.2 times sine of 23 degrees. And that's equal to 16.10 meters per second. And then the only other thing we have to check, we have to be careful here. In the first quadrant, it's not much of a big problem, but we'll see later. I'll do another example in a few minutes where if it's in a different quadrant, you have to be careful about the sign, the SIGN of the particular components. So in this case, see how bx is directed towards the right? So its sign, SIGN, is going to be positive, and then by, since it's directed up, is also going to be positive. But that's only true because we're in the first quadrant, right? If we were in a second quadrant, the x component would be negative and the y would be positive. In the third quadrant, both components would be negative. In the fourth quadrant, the x would be positive, but the y would be negative. So you have to be careful and attach the correct sign at the end based on what quadrant you're in. Okay, here's another example where we have to worry a little bit more about the quadrant that we're in. Okay, let's say I'm given a vector r, and let's say the magnitude of r, I'll use the double vertical lines, is 230.5. I'll say it's a force vector, so it's newtons. And let's say the direction of r, so theta, measured from the positive x counterclockwise, let's say is 215 degrees. And I want to find the components, right? I want to find rx and ry, the two components of vector r. Okay, so let me draw this out first. So here's my standard Cartesian coordinate system. Now, 215 degrees is going to be in that third quadrant, right? Because this would be like 180 to there, and I have to go a little bit more. So it's going to be somewhere in that third quadrant. Okay, so that's vector r. So this is 215 degrees. And again, what's my goal? My goal is to find the x component. So if I project this go from the tip, project it onto the x-axis, that's going to be this component. I'll do it in red. So this is like Rx. And if I project this onto the y axis, then I want to find the y component, which is Ry. Right? And note that the SIGN of those two components are both going to be negative, right? Because Rx is going to the left, so it's negative, and Ry is going down, so it's negative. Okay, now to make things easier, right, we could actually, in fact, use the 215 degrees directly, but it gets more confusing if you do it that way. I think it's easier just to use the reference angle. Remember, the reference angle is the angle that the vector makes with the x-axis, so that angle right there. So how do I find that? Well, if it's 215 all the way to here, then if I subtract 180, that should give me the reference angle, right? So for the reference angle, I'm going to find it just by taking 215 minus 180, and that turns out to be 35 degrees. So this angle right there is 35 degrees. Okay, so let me extract out that right triangle. And again, you always extract out the right triangle that contains the reference angle. So that right triangle right there. So I'm going to draw it separately. I know that this angle is 35 degrees. I know the length of the hypotenuse, right? Because that's the magnitude of r. What was that? That was 230.5. That was the magnitude, right, of the force. This is really newtons. And I'm looking for Rx and Ry. Now, since I have it just drawn as a triangle now, and with a triangle, right, we can't really have negative lengths of the legs. So we assume that Rx and Ry are positive, but then we attach the correct sign later, SIGN later, based on the direction of Rx and Ry. Okay, so we're just getting the magnitude now, and we'll attach the correct sign later. Okay, so let's do Rx first. Well, how does it relate to the angle? It's adjacent, right? This is next to, Rx is next to the 35 degrees, and the 230.5 is a hypotenuse. So what trig function relates adjacent and hypotenuse? That's cosine. And if you always use the reference angle, to find the x component, you're always going to use cosine. To find the y, you're always going to use sine. Okay, so that's something you'll find after doing this a few times, and then you could save a little time by knowing that. So cosine of 35 then is going to be Rx over 230.5. And if I multiply both sides by 230.5, I'm going to find that Rx is equal to 230.5 times cosine of 35 degrees. And that turns out to be 188.8. newtons. And then sine of 35 is going to be Ry over 230.5, right? Because it's opposite. And now if I multiply both sides by 230.5, I'm going to find that Ry is equal to 230.5 times sine of 35 degrees. Notice I'm leaving a little blank in here just in case I need to change the SIGN, the sign. And this is 132.2 newtons. Now, let's go back to the original picture. And again, because Rx is pointing to the left and Ry is pointing down, right? The vector's in that third quadrant. Then both of these components must have what for their SIGN? They must both be negative. Okay, so that would be the correct answer, right? They have negative signs. Okay, what if I give you the components and I ask you to find the magnitude and direction of the vector? Okay, let's do a problem like that. So let's say I tell you that we have a vector C, And let's say I give you the fact that Cx, the x component of C, is 5.5 meters. Let's say it's like a displacement or something. And let's say Cy is -4 meters. So I'm giving you the x and y components. And what we want to do is we want to find the magnitude of C and the direction. And I'll assume the direction is measured from the positive x counterclockwise, right, all the way around. Okay, so let's draw this out. Well, in order to have an x component of 5.5 and a y of -4, C must be in the fourth quadrant, right? Because, so think about this, right? If I want my x component to be, let's say that's 5.5, so Cx is equal to 5.5 meters, and then Cy is -4, then that means the actual vector must have been this vector. That goes from the origin to the other side right there. So that must have been vector C. Okay, so my goal is to find the magnitude, so the length of that vector. And then at first, I'm going to have to find this reference angle first. Here's where our inverse trig functions will come into play, right, to find the angle. And then once I find that angle, I can find the theta, the one I really want, is measured from the positive x counterclockwise all the way around, right? So I really want to give theta at the very end. But once I find phi, it's easy to find theta. In this case, I would just do 360 minus phi, right? And that would give me theta. Okay, so let me extract the triangle that contains the reference angle. So that's going to be this triangle right here. I'll extract out that triangle separately. So this is 5.5. Remember, the y component is -4, but when I talk about a triangle, there's no such thing as a negative length. So we just call this 4, but we know it's -4 because the actual component is -4. But that length itself is just 4. And I want to find this side length. This is my magnitude of C, right? And I want to find that angle theta. So ultimately I can find, phi. So ultimately I can find theta later. Okay, how do we find, let's do the length first. How do we find the magnitude of C, the length of the hypotenuse? Well, can't we just use the Pythagorean theorem, right? Remember, in general, if you have a right triangle, that one leg squared plus another leg squared equals the length of the hypotenuse squared. A squared plus b squared equals c squared. So in this case, the way to say that is my x component squared plus the y component squared is equal to the magnitude of c squared. So if I want to find c, it's going to be the square root, and by c I mean the magnitude. You could also write it like that, right? It's going to be the square root of cx squared plus cy squared. So in this case, it's going to be the square root of 5.5 squared plus 4 squared. Right? Or you can even use -4 because you're squaring it, so it doesn't matter. And if you do that, you're going to get that the magnitude of C is equal to 6.8. And it had units of meters, right? So it was a displacement. Okay, what about the angle phi? Let's find phi first, and then we'll go back later and get theta. So phi, well, I guess I could use any of my trig functions now, right? Because now that I know the hypotenuse, but let me use the original values that I had. So 4. So how does this side 4 relate to the phi? It's opposite. And how does the 5.5 relate to phi? It's adjacent, right? So if I use tangent, I know that tangent of phi is equal to opposite 4 divided by adjacent 5.5. But I don't want tan of phi, I actually want the angle phi, right? So how do I extract out the angle? Here's where we have to use our inverse tangent, our arctangent. So I have to take the inverse tangent or arctangent of both sides. So inverse tangent of tan of phi, that just gives me phi, right? That was the whole point, right? The inverse function undoes the function, gives you back the argument. And then the right-hand side, this you have to do in your calculator. Make sure that your calculator is in degrees. And you're going to find that you're going to get 36.03 degrees. Okay, so this angle right here is 36.03 degrees. But then ultimately, we want the angle, we want this angle, right? From the positive x counterclockwise, which I'm calling theta. So how do I get that? Well, if I do 360, which would have been all the way around, minus phi, that's going to be the correct angle for theta. Right, so theta, which is the one I really want, is going to be 360 minus phi. So 360 minus 36.03, and that is equal to 323.97 degrees. And often they will, like questions will ask you to give the final angle measured from the positive x-axis counterclockwise. Okay. The other way you could do this is if you didn't want to find theta, if you just want to use phi there, you could use phi, but then you have to give a little more information to say that it's in the fourth quadrant. You could say, you know, the direction. First of all, you could say C had a magnitude of 6.8 meters and it was at 323.97 degrees. That's one way of saying it, right? That in that case, we're using the actual angle from the positive x counterclockwise. Or this will also give me enough information. I could say C is equal to 6.8 meters at 36.03 degrees south of east. Right? If I start east and go south, then that would be 36.03 degrees. And that also tells me that I'm in the fourth quadrant. Or you could even say negative 36.03 degrees, and that means you're measuring clockwise, right? So there's many, many different ways of giving the angle. As long as you have enough information to determine which quadrant the vector is ultimately in, then that'll be fine. Okay, now what I want to talk about is adding vectors. Let's look at how you would add vectors together. So adding vectors. And actually first, let me do this graphically. So if I have a vector A, so this is my vector A, right? It has some magnitude, right? It has a length, it has some orientation, some direction. And then I have a vector B, let's say B looks like this. So it also has some length and some direction. And I want to add those two vectors together graphically, and then we'll do it analytically where we use, you know, actual values. We'll do it mathematically. So graphically, just to get an idea of like what's going on, is the following. You would start with vector A. So I'm going to draw a coordinate system first. Then I would take A and I would slide it. So literally you're going to maintain the same orientation, the same length, and you're going to slide it so that the tail of A is at the origin of the coordinate system. Okay, so if I redraw this, right, if I slide this and maintain the same length, same orientation, it's going to look something like this. Right, so that's vector A. By the way, mathematically, it doesn't matter if you move the vectors around as long as you maintain the same length and the same orientation, the same direction, then the vectors are considered to be the same. Okay, you can slide them around however you want as long as you maintain the same length and the same orientation. They're considered to be the same vectors. Then what you would do is at the tip of A, so where the arrow is, right, at the tip of A, I'm going to draw on a new coordinate system. I'm just going to dash this in here. It's a new XY coordinate system. And now I'm going to slide B so that the tail of B is at the tip of A. So this was the tip of A. Now I'm going to slide B. So the tail of B is at the tip of A. So it'll look something like, let's say like that. Okay, so I'm basically adding tip to tail. So I'll say graphically, we're going to add tip to tail. And now finally, to get the resultant vector, to get A plus B, I simply draw a vector from the tail of A, so that's from the origin, to the tip of the second one, which is the tip of B. So this would be my vector I'll call R, resultant vector, and that R there is A plus B. So you add vectors together by adding tip to tail, tip to tail, tip to tail. Okay, so R is equal to A plus B. And then of course R has some magnitude, its length, and it has some direction. You can measure the angle theta with respect to the x-axis. All right, so let me just show you one more example of adding vectors graphically, and then we'll get into how you add them mathematically, which we call the analytical method. So let's say I have vector A, let's say it looks like this. And then let's say B looks like this. And then C looks like this. And I want to add A plus B plus C graphically to get some resultant vector, which I'll call R. Okay, so how do I do that? Well, let me draw a picture. Here's my coordinate system. Right, so X, Y. I would start with A, right? So I have A, and I would slide it so that the tail of A is at the tip of the coordinate. The tail of A is at the origin of the coordinate system. So, and I'm going to draw it out. So I'm kind of sliding it so it's like right there. It's hard to draw exactly the same length. I guess a little longer, right? When you're doing this by hand, if you do it on a computer, you can get exact. Let's say that's A. Then I would take B, and I would move the tail of B to the tip of A. Okay, again, some people like to draw on like a little coordinate system here at the tip of A. Then I move B so that it's at the tip of A, so it would look like this. Let's say that's B. Then I would draw another little coordinate system at the tip of B. And then move C so that its tail is at the tip of B. So let's say it looks like this. So this is C. And then what's my resultant, A plus B plus C? Well, it goes from the tail of A, so from the origin, to the tip of the last one, so the tip of C. So this, that vector would be my A plus B plus C. That's my resultant. And then, of course, you could measure the length of R, and if you wanted to measure the angle from the positive x-axis, that would be this angle, right? So it has a magnitude and it has a direction, the resultant vector. So that's graphically. I'm not going to spend too much more time talking about this graphically, although this is really important if you guys end up taking physics with me, or Dr. O'Brien or Dr. Satz in the fall, then you will definitely see vectors. You'll see a lot of vectors, and we will do things where we add vectors both graphically and analytically, right, mathematically. Okay, so that's graphical. How do we do this analytical? Well, to add vectors analytically, right, mathematically, all you have to do is you add the components together. So to add, that's why it's so important to find the components of each vector. So to add vectors analytically, just add the components together. Okay, so here's an example. Let's say I'm given that vector A is 10 newtons, so it's going to be a force vector, at 180 degrees. And I'm given vector B is 5 newtons at 30 degrees. And I want to find the sum of those two, which I'm going to call R, which is A plus B. I'm going to add them together and get the resultant vector. Think of R as like the resultant. It's the resultant of summing them together, A plus B. Okay, so first thing we have to do is find the components of each vector. Find the components of vector A and the components of vector B. So we need to do that first. Okay, so how do we find the components of vector A? I would draw a picture, right? So draw a Cartesian coordinate system, so XY coordinate system. And 10 newtons at 180 degrees. Well, 180 degrees means that vector A is going along the negative x, right? It's going in the negative x direction, so this would be vector A. We know its magnitude is 10 newtons, and we know the angle measured from the positive x-axis counterclockwise is 180. So this angle right here is where we get the 180. Okay. So in this case, we don't even need to use trig to get the components. We can just look at the picture and get the components. What is the x component of A, and what is the y component of A? So how much of that vector is in the x direction? Well, actually, all of it is, right? But since it's going negative, it's going to be negative 10. Right? The x component of A is negative 10 newtons because all of it is in the x direction, but it's negative. And then how much of that vector is in the y direction? If you project that vector onto the y-axis, none of it, right? It's all in the negative x, none in the y. So the AY is going to be 0. Okay? One of the notations that MyOpenMath uses, so let me mention it here because you'll have to deal with this. It'll write it this way. It'll say A is equal to, then they use like triangular brackets, and then they list the x component first and then the y component. So that's another way of writing A. So the first is like AX and the second is the AY. Okay, just so you're aware of that notation that comes up in MyOpenMath. Okay, now the B, so that was 5 newtons at 30 degrees, so something like this. So again, the magnitude of B is 5 newtons, and then the angle was 30 degrees. So that means this angle is 30 degrees. And I want to find BX and BY. So I need to find BX. And then this one BY. Okay, so we already talked about how to do this, right? Extract out your right triangle that includes the reference angle. So it's going to be this triangle. I know that this angle is 30. I know that the magnitude, the length of the hypotenuse, is the magnitude of the vector, so that's 5, right? It's really 5 newtons, has units in this case. And then this is bx, and then this side is the same length as by, so you can call that by. And then how do we find bx and by? We use our trig functions. Well, since bx is adjacent to 30 degrees, and the 5 newtons is the hypotenuse, which trig function relates adjacent to hypotenuse? That's cosine. Right? Remember I said the x component, and you guys will, the more you do these problems, you'll find that as long as you use a reference angle, the x component will always involve the cosine, so there'll be 5 times cosine of 30, and the y component will always involve the sine, so 5 times sine of 30. And they're both positive, right? Remember, we have to also get the correct SIGN, but since we're in the first quadrant, bx is going to the right, by is going up, so they're both positive. So these turn out to be 4.33 newtons and then 2.5 newtons. If you want to write it in the format or the notation that my Open Math uses, it'd be bracket 4.33, comma, 2.5. Okay, so now to add vectors together, we simply add their components together. So there's a couple ways you could do this. You could, some people like to make a table, right? Let me do that first. So you could make a table just to organize your work. So I have x component, y component, and I have vector A, vector B, and I want a resultant vector R. So what's my x component of A? Well, that was -10, and my y was 0. And in B, my x component was 4.33, and my y was 2.5. So now to add the components together just means add down the column, right? So for the x component, if I add -10 plus positive 4.33, I'm going to get -5.67. So this is like my Rx, this is like my resultant x. And then 0 plus 2.5 is obviously 2.5. This is like my Ry. Okay, so now I have my resultant vector components, right? I know Rx, I know Ry. By the way, the other way you could have done this is you could have used the notation that's used in my Open Math. Let me just show you that real quick, and then we'll finish up this problem. So since A was -10, 0, and then B was 4.33, and then 2.5. If you want to add components together, remember this is really the same as AX, AY. This is the same as bx and by. So for the resultant, I could just add, well, I need the x component of A, the -10, plus the x component of the B, 4.33. And for the y, I need the y component of A, which is 0, plus the y component of B, which is 2.5. And of course, I'm going to get the same thing, right? I'm going to get -5.67 and then 2.5. Right, so either way, you can do it using the notation, using the triangular brackets, or you can make a little table, right, where you have columns of x component, y component. It's up to you. Okay, so now we're almost done. In fact, we know a lot about this vector because we know the components, but let's write the final answer in terms of the magnitude of r and the direction of r. Okay, so I'm going to draw a picture that represents the vector r now. So I know my x component is negative. So this is like Rx is negative 5.67. So I'm going to the left. And then Ry is positive 2.5. Right? These really have units of newtons. So that means that my vector r must have been this vector, right? The only vector that can have those components is this vector that goes from the origin out to here. So that's r. Okay. So I want to find the magnitude of r. Well, that's easy. I can just use Pythagorean theorem, right, to find the magnitude of that vector. And I want to find the direction. So ultimately, I want to find this angle from the positive x measured counterclockwise. So the angle theta. But it's going to be easier to find the reference angle, which I'll call phi, to find the reference angle first. Okay, so let's do the magnitude first. I'm going to extract out the right triangle that just includes the reference angle. So this is phi. This is what I'm looking for, the magnitude of r. I'll write it this way. And I know that the length of this side, the component is actually negative 5.67, but when I draw it as a triangle, it's just a positive length of a leg, so I can just call this 5.67. And this one I can call 2.5, right? This is my right triangle. Okay, so how do I find the magnitude? I use Pythagorean theorem. So this is going to be the square root of 5.67 squared plus 2.5 squared. And if you work that out, you're going to get around 6.2 newtons. Okay, so that's my magnitude. And then how do I find the angle? Well, I know that tan of theta is equal to opposite 2.5 over adjacent 5.67. So that means theta itself must be the inverse tan, right? I need to take the inverse tan of both sides. Well, the inverse tan of theta gives me theta, so I just wrote theta on the left-hand side. And the right-hand side, I have to do this out on my calculator. And I'm going to get 23.8 degrees. Now, you could stop right there and say, okay, it's 23.8 degrees. And if I say, like, north of west, so N of W, meaning north of west, that will give me enough information, right, to figure out that I'm in the second quadrant, the direction of that vector. Or if I really want to find this angle theta here, then how would I find it? Well, if I go from here to here, that's 180. So if I do 180 minus phi, that will give me the angle theta. So either way, both ways will give you enough information. Sometimes the problem will specifically ask for a particular angle, measured with respect to whatever, the x-axis counterclockwise or whatever. It'll ask for a specific angle. So if you want that angle with respect to the positive x-axis counterclockwise, the theta, then that would be 180 minus phi, right? Because we're in that second quadrant. So this would be 180 degrees minus 23.8. That turns out to be 156.2. Okay, so now I have my answer, right? My resultant vector is going to be 6.2 newtons at 156.2 degrees. Or 6.2 newtons at 23.8 degrees north of west. Right? In this case, I just used the angle as we normally measure it from the positive x counterclockwise. Great. Okay, let's do one more addition problem. It's a little harder. It has three vectors that we want to add together. So let's say I want to add vector A, which I'm going to say is 2.5, also assume it's a force vector, 2.5 newtons at 30 degrees. Vector B, let's say is 10.2 3.25 newtons at 180 degrees. And C is, say, 3.4 newtons at 20 degrees. All right, so first find the components, right? So vector A. (2.5 newtons), that's the length of this. This is 30 degrees, right? And I want the component, so this is going to be like AX, and then AY. They're both positive, right? Because X is going to the right, Y is going up. And we know that you can work this whole thing out using trig, but you're gonna find that this is going to be, well, let me write down the magnitude. So the magnitude of A was, what was it? 2.5. So this is going to be 2.5 times cosine of 30, and the Y component is going to be 2.5 times the sine of 30. Right, so 2.5 times cosine of 30 is 2.17. And then 2.5 times sine of 30 is 1.25 newtons. If you want to write it in that MyOpenMath format, which, by the way, a lot of like calculus textbooks and pre-calc textbooks will use the same square bracket format. This is going to be positive 2.17 and then positive 1.25. Okay, so that's A. B, actually B is really easy, right? I can squeeze, let me just squeeze in B over here. It's 10.25 newtons at 180 degrees. So it's going along the negative X direction, right? Because this is 180. So this is B. And that also turns out to be the X component, except we know it's negative. So it's negative 10.25 newtons. And then what is the Y component? How much of that vector is in the Y direction? None of it, right? It's all in the negative X, nothing in the Y. So BY is 0. So if I want this in the bracket notation, this would be negative 10.25 comma 0. Okay, and then C, kind of like A, right? It's in the first quadrant. We know that the magnitude was 3.4 newtons. We know that this angle is 20 degrees. And I want to find the X component and then the Y component. So CX, CY. And it looks like they're both going to be positive again, right? So again, we know that cosine of 20 is, if I extract my right triangle, I kind of skipped steps on A. Let me just do it more carefully for C here. So this is 20 degrees. I know that the hypotenuse is 3.4, right, newtons. This is CY. This is CX. So remember, cosine of 20 is going to be adjacent CX over hypotenuse. So therefore, if I multiply both sides by 3.4, CX is going to be 3.4 times cosine of 20 degrees. Right? That's why I keep saying, as long as you use the reference angle, the X component will always involve the cosine, the Y component will always involve the sine. Okay, in this case, this is equal to 3.19 newtons. And what is the sine? It's positive, right? Because CX is going to the right. And then for the Y, well, I know that sine of 20 is equal to opposite, which is CY over hypotenuse. Therefore, if I multiply both sides by 3.4, I'm going to get CY is equal to 3.4 times sine of 20. And that's equal to 1.16 newtons. And again, it's positive because Cy is going up. So then C, written in bracket notation, will be 3.19 comma 1.16. Okay, so you could make a table. Let's just add them using the bracket notation. So now I want to find my resultant vector by adding A plus B plus C. So again, just to remind you guys, remember A was 2.17 comma 1.25. B was negative 10.25 comma 0. And then C was 3.19 comma 1.16. Okay, so R, which is A plus B plus C, is simply going to be the sum of the x's, right? So this is going to be 2.17 plus negative 10.25 plus 3.19. And then the y component of R is going to be the sum of the y components of A, B, and C. So this would be 1.25 plus 0 plus 1.16. So this ends up being negative 4.89. And then the y is 2.41. All right, so let's draw this. Looks like we're going to be in the second quadrant again. Right, because the x component is negative. And the y is positive. So our resultant vector was in that second quadrant. So it looks like something like this. Oops, crooked there. So something like that. So that's R. And I want to find the magnitude, and I want to find the direction. So again, ultimately I probably want to find this angle, but I want to first find reference angle theta. Okay, so let's extract out that right triangle. So this is theta. This is what I'm looking for, right? The magnitude of R. And I know that this length, the RY, is 2.41. The RX was negative 4.89, but the length here is just 4.89, right? Because it's just a triangle now. And how do I figure out the magnitude of R, the hypotenuse? Pythagorean theorem, right? So that's just going to be the square root of 4.89 squared plus 2.41 squared. If you work that out, it's going to be 5.45 newtons. And then how do I find the angle? Well, I know that tan of phi is going to be opposite 2.41 over adjacent 4.89. So therefore, if I take the inverse tan of both sides, I'm going to get phi is equal to the inverse tan of 2.41 over 4.89. Plug that into your calculator, and you should get 26.2 degrees. Again, you could stop there and say that R was 5.45 newtons at 26.2 degrees north of west, and that would be enough information. But now if we really want to find theta here, then we have to subtract that phi from 180. Right, so if I really want theta, then I want 180 minus phi. So 180 minus 26.2, and that's going to be 153.8 degrees. So then I can say my resultant vector, the sum of those three, A, B, and C, A plus B plus C, is 5.45 newtons at 153.8 degrees. Or 5.45 newtons at 26.2 degrees north of west, right? That would also be fine. Okay, great. So actually, I think that's it for this video. I'm going to do one more video where I do some specific examples that are related to the homework for this section. Since the myopen math, the notation is a little bit different with that, with the triangular brackets. Let me do a couple of problems that are related to the myopen math homework problems. That'll be in the next video. Thanks.